Hi everyone, welcome to the next lecture in the flight mechanics series, and we're looking today at deriving the last set of relationships that we need to fully describe unconstrained flight in 6 degrees of freedom. So let's have a look at what we've done so far. We have got the translational equations of motion. Oh, that's okay, so we've got the translational equations of motion. You might wonder why I switched to this white on black, and it's because I can move things around and I can appear behind my notes so I can talk about them a little bit better. So let's just talk about what we have here. We've got the left hand side. This is the sort of the MA, so remember this right hand side is the absolute acceleration. And we got this from Coriolis theorem. So we derived Coriolis theorem when we got this, and we can see that, for example, the x component of the absolute acceleration has got the first time derivative of the absolute velocity, and then these cross-coupling terms that appear because of the cross-coupling of rotational motion and velocity in axes other than the x direction. So we've got pitch rate and heave velocity, and we've got sideward velocity and yaw rate occurring here. So that's the x direction, and you can similarly go through and see the same with these other two. And then in terms of the aerodynamic forces, we put the aerodynamic forces into body axes. So we've got the component of weight. Remember, weight's defined in Earth axes. So we took it through the Euler transform. So we've got 3 Euler angles: yaw, pitch, and roll, which are psi, theta, and phi. So we've got these ones here. We've then got the aerodynamic forces. So we've got the component of drag acting in the x direction, rotated through the angle of attack, sideward component, and we've got the drag through the again through the angle of attack, and then we've got the same with lift here. And the last components, we've got the 3 components of the propulsive forces. So this describes our translational forces, which give us not just the translational forces, the relationship between translational accelerations and the translational forces acting on the aircraft, or the forces acting in the x, y, and z direction. So this is our translational equations of motion. We went through a similar exercise and got the rotational equations of motion. Okay, so we went through a multi-step process where we defined this concept called angular momentum, which we've spoke about before, and we then said that the sum of the applied moments on the aircraft is equal to the rate of change of the absolute angular momentum. So we defined linear momentum, turned it into angular momentum through the cross product of position and the linear momentum. And then we worked out the time derivative of that, again using Coriolis theorem. So we ended up with all these cross-coupling terms, and we then reduced the number of these cross-couplings by saying that our aircraft is symmetric in certain planes. So for example, our IZY is small in components to some of the other cross-couplings, so it's really only the IXZ that we end up keeping. Okay, so we've got the rotational equations of motion. So we can say that the applied rolling moment, for example, gives us a direct roll rate, or a rate of change of roll rates, and the constant of proportionality is the moment of inertia in the x direction, so the roll moment of inertia. We've then got this coupling between pitch rate and yaw rate, and that's then proportional to the difference between the direct moments of inertia of the 2 axes that are unrelated to roll. So z-axis is the yawing moment of inertia, y is the pitching moment of inertia. Okay, so remember that these ones here are the gyroscopic precession terms, with gyroscopic precession, and then we've got these other cross-coupling terms here. And there are far fewer of these than we would have had we not got rid of all of the other products of inertia that weren't IXZ. So we've got our rotational equations of motion, and we've got our translational equations of motion. There's one more set of relationships that we need to derive, but thankfully they're kind of simple, and we've already got all of the things we need to do to actually describe them. So let's just describe what we need. We've got two different measures of sort of displacement or angular motion. So we've got the aircraft body rates, and these are a vector of angular rates. So this is omega is P, Q, and R. Now these are the rates as measured in the body axes, or as would be experienced in body axes. So if our aircraft has got a rate gyroscope in it, which it probably does, then that rate gyroscope is directly measuring these terms up here, measuring P, Q, and R. Now, to define aircraft position, we use the Euler rates. Oh, my. Okay, so everything just stopped working there, and I had to mess around with various things underneath my desk to get all these cables working. Sorry about that, but we're back now. So we've got these, again, these aircraft body rates. These are the ones that would be measured by a rate gyroscope in aircraft body axes, and these are the ones that you would feel in the aircraft. So you feel this pitch rate, etc. I'm not going to go too much into pilot perception in this module. We'll talk a little bit about that in module 5, but these are the absolutes. The aircraft body rates as experienced and would be measured in a rate gyroscope. To define aircraft position, we use the Euler angles, or to define, the aircraft angular position. So this is the aircraft attitude. Okay, so let's give this symbol, let's say this is an uppercase vector phi, and this is therefore equal to, the roll is psi, and then we've got theta, and we've got psi is the yaw. So these are the angles that define the relationship between body axes and earth axes. And we defined a transformation that was a quantity in body axes. No, sorry, I've written that as a matrix, that should be a vector rather, is equal to a transformation matrix multiplied by a quantity as measured in earth axes. So this was a 3x3 matrix. It's a combination of those three different Euler matrices, T1, T2, and T3. So this takes quantities as defined in earth axes and puts them into body axes. So it's going to be useful for translating aircraft velocities into earth velocities, and we'll use that. We actually have to use the inverse of the T matrix to go the other way around. And we're going to use those in some examples that are going to come in the following lectures. We can't use this though to do the relationship between body rates and Euler rates, because the Euler rates are all defined in three different axes sets. Okay, so if we remember how the relationship works, this is pretty cool. This was a test of me making a different woodworking joint. Worthless for this class in terms of how that was made, but it's useful because I've got a right-handed axis here. So the rotation order that we went. So remember, if this is my body axis, this is aligned with earth axes at present. So to go from the 2, we go through yaw, pitch, and roll. I should probably flip the camera when I'm doing this actually, because that's going to be a little bit confusing, because that looks left-handed, but it's actually right-handed. So let's switch this over. Okay, there we go. So this is my right-handed axis set now. So the rotations that we go through are yaw, pitch, and roll. Then the angles that we go through again, so remember this is psi, theta, phi. This means that psi is defined in Earth axes, theta is defined in this new intermediate axis set, and then phi is defined in the second new intermediate axis set. So to do that transformation and to get a transformation from these to these, we need it to be part of those 3 successive rotations need to be defined in those individual axis sets. I think I've just described that fairly horribly there. We'll say the transformation also, let's just go back a second as well. I couldn't, even if that transformation matrix worked, I couldn't use it to go from these to these. What I would be able to do, let's say what we'd actually want is the rate of change of this attitude vector. So that's phi dot, theta dot, and psi dot. Okay, we want a relationship between the rate of change of these and the body rates. So we want because we cannot say we don't have P, Q, and R. Okay, and the reason for this is that they're defined in those different axes sets. So let's just write this in words. The reason the transformation, the Euler transformation cannot be used to convert body rotation vector and the rate of change of the Euler angles is that T relates so the body rates are all defined in body axes. There's a clue in the name there. So then we've got our Euler vector. Let's just say, let's not bother the time rate of change. We've got so again, because they're defined in 3 different axes sets, we need to come up with a relationship that's going to help us convert between the 3 of them. Okay, so we're going to do it separately for each of them, and then we'll just add up the 3 parts. So we're going to define an increment to the body experience rate due to the Euler rates, each one of them, and then we're going to add them together. So we're going to define an increment due to each of those Euler rates, and we're just going to add them up. And so we're going to say that we want one due to, what order are we going to, let's go in. So we're going to work out some sort of vector like this. So this is the change to, well, let's just say it's the body, nope, let's go forward. Body angular vector due to Euler rate. And so there's going to be three components. So a body, an Euler rate will have three components to it. So we'll have a P psi dot, a Q psi dot, and an R psi dot. Slightly different nomenclature than I use in the online notes, but all we're going to use is the product of this part, not so much the. I want you guys to understand the derivation. You might be asked to complete some of this in an examination, but it doesn't really matter what we're using in terms of these. What I'm writing these as, which I can't point to at the moment, because we're just using them to come up with this transformation. So let's think about how we're going to do this. So the first one, we're going to do them sequentially. So this one is going to be some function of the total transformation matrix. And this one is easy to do. So this is going to be equal to, all three matrices, T3, T2, T1 multiplied by our Euler vector. So we've got 0, 0, and then Euler rate. So if we go back to our total transformation matrix, which actually I haven't got written anywhere here, let me just write the whole thing down. Again, I'm probably going to have to fast forward through this because it's, in fact, I'm going to be a little bit cheeky, and we can see that we're not going to need, if I put down the whole transformation matrix here, I don't need it. All I'm going to need is the rightmost column of it. So I need the rightmost column. I'll trust you to go through the notes and look up the big transformation matrix. I don't want to write the whole thing down. I'm just going to write the product of the rightmost column and these three things here. Okay, so we can put that down. And for us, that's going to be equal to minus psi dot sine theta, psi dot sine theta, cosine theta, psi dot cosine theta, sorry, cosine psi, cosine theta. So let's just think about what this is here. This is the body rate experienced due to a rate of change of heading, or Euler psi. Okay, so let's think about whether this makes sense or not. So heading is effectively the orientation of the body axes within Earth axis, so it's where the aircraft sort of body is pointing. So let's think about if this makes sense. So if we have no pitch, then if we've got no pitch, then these bottom two terms go to 1. So let's say here these cosine theta just gives us 1 in both cases. Then we're going to think about the other two terms as induces. So let's just repeat this line down here. We've got P I dot Q psi dot, and R psi dot here. So let's just remind ourselves what these mean. I'm going to move, I can't move that away annoyingly. Let's erase these. Okay, so this is then we can think about how this works. So it's this this first top term here. This is an experienced pitch rate due to a rate of change of heading, and this only occurs at non-zero pitch. So let's think about what this means. If my aircraft is got a rate of change of heading, it's effectively flying in a circle. So aircraft is flying in a circle with wings level. In fact, it doesn't matter whether wings level because there's no psi in this at all. What this is telling us is that if there is a pitch attitude of 0, there is no experienced roll rate, okay, when we're flying in a circle. Now let's just think about the opposite example. When we've got the pitch is equal to 90 and the aircraft is still flying in that same circle, the aircraft is effectively feeling like it's turning round, okay, so it's got an experienced roll rate on the aircraft. So we're going to produce this whole matrix, and I want you guys to be able to think about what these different terms mean. This is where it's handy to have an aircraft model in this case. So we've done our first one here. We're going to do the same for the other two now. So we're going to come up with the one due to pitch rate. So remember, for this first one, we had to go through all three of the Euler angles. We're now going to go through and do the same for pitch rates. So the vector that we want is omega due to theta dots, and we're going to get three components: p theta dot, q theta dot, and r theta dot. So pitch rate is an intermediate 1. So this has already gone through the first Euler transformation matrix. So the relationships that we're going to need, this is going to go through the second and the third Euler rotation matrix. Okay, and then our Euler pitch rate is 0, theta dot, and 0. So let's just remind ourselves of what these two rotation matrices are. I need to dig them out. I've got them written down here. Okay, I'll do some prep for this, so just write down my matrices. Okay, so our matrix T3 is 1, 0, 0, 0, 0, cosine phi, sine phi minus sine phi, cosine phi, and then our second matrix, cosine theta, 0, minus sine theta, 0, 1, 0, sine theta, 0, cosine theta. And we're going to multiply this with 0, theta dot, and 0. Okay, whenever you're doing the Euler matrices, you can always just do a quick check that you've got the right one. So let's remember our roll phi is defined around the x-axis, so we have a unity in the x by x. Okay, so the first row, first column is a 1. That makes sense. And again, second one here, pitch is defined around y. So in row 2, column 2, we've got a 1, and that makes sense. So just check when you're going through these that you've got the right expressions. So we'll do this multiplication first. So let's copy down this matrix because I don't want to write it down again. So if I do the multiplication here, then we're going to end up with, so nothing in our first column, so nothing in our first row. Then we're going to have 0 multiplied by 0, 1 multiplied by theta dot, and nothing multiplied by theta dot, and then sine theta 0, 0 multiplied by theta dot, cosine multiplied by 0. So that was an easy multiplication to do. And now we can get our next terms out. We should be able to see fairly easily that there's going to be nothing in our first row. Second row is going to be 0 times 0 theta dots multiplied by cosine phi, and then nothing. And then the third row is going to be minus theta dot multiplied by sine phi. Okay, so let's just remind ourselves what we've got. This is omega due to a rate of change of the Euler pitch rate. Okay. Body rate due to Euler pitch rate, and then the last one that we need to do is get the rate of change of body rate due to an Euler roll rate. Okay, so we're looking for phi dot is our input, and what we want to get is omega due to phi dot and this is just going through the third transformation matrix, because remember that phi is in intermediate 2, which has already been through the first and the second Euler rotation matrices. So we only need to use the third one now. So T3 multiplied by, and the roll rate is in the first row, 0, 0, and we've already got our expression for the third matrix. So let's just copy this down again. Okay, so this should be fairly instructive, that you'll see that all we have here is theta dot, 0 and 0 here. So what we can now get is we can add up the contribution of all of these to our total angular rate vector. So we can sum these contributions. So our angular rate vector is equal to the contribution due to Euler yaw rate plus the contribution due to Euler pitch rate plus the contribution due to Euler roll rate. So for our purposes, that is, let's write all of these down. We've got psi dot sine theta, psi dot sine theta cosine theta, and psi dot cosine, sorry, that's a psi, not a phi, cosine theta. And the next one is nothing, theta dot cosine phi minus theta dot sine phi. And the last one is nice and easy. All we have is our phi dot 0, 0. Add these all up together. In fact, let's put this straight into a transformation matrix. That's just going to be easy to do. Okay, so we're going to have a 3 by 3 matrix. So in our first expression, we've only got, well, let's have a look, see what we have here. So we've got, in the first thing, we've only got a 1 here. Okay, and we've then got nothing due to pitch rate in the first row. So we've got a 0 here, and then we've got sine theta multiplied by the Euler rate. Okay, second row, we've got an expression due to, we've got nothing due to the Euler roll rate, and in fact the same we can see in the body yaw rate, we've got nothing due to Euler yaw rate. And then in this term here, so this is an experienced pitch rate due to a body, sorry, due to an Euler pitch rate. So we've got cosine multiplied by the roll angle here, and then we've got this expression here. So this is, we need a sine, psi, cosine theta here. Okay, and then in this last one, we are looking to see, so this is body yaw rate. So we've got nothing due to the body roll rate, which we already know. We've then got this expression here, represents the body yaw rate due to Euler pitch. So we need a minus sine multiplied by the roll angle. And we've then got the last term here. This is the body yaw rate due to Euler yaw rate here. Okay, so this is our matrix that does the transformation between Euler attitude rates and body angular rates. Okay, so if we want to do any relationship that relates our measurements taken in body axes in terms of the angular rates, and we need to convert it to an attitude by integrating over time, then we need to use this matrix to, or we actually need to use the inverse of this matrix. This matrix is not orthogonal, but I'll just give you the inverse anyway, or I'll leave it as an exercise for you guys to show. We can end up saying that phi dot, theta dot, and psi dot is equal to sine phi tan theta, cosine phi tan theta, cosine phi minus sine phi, sine phi on cosine theta, cosine phi divided by cosine theta. Okay, so this one gives us if we have body angular rates, which is what we measure, and we want to convert it to something we can use to determine the position, so the attitude. So we then want to get these and then integrate them to give us the Euler angles. Then we need to use this matrix here. Now you might see a bit of a problem here because we've got terms that can be 0 in denominators. Okay, so the matrix becomes singular in this case. Okay, and that's an issue. It means we can't relate them. This is a phenomena called Gimbal lock. Okay, which means we can't relate the experienced body rates back to Euler attitude rates using this method if we've got very high pitch angles, or effectively if we have Euler, if we have a pitch attitude of 90 degrees. So if this occurs, then this is just a limitation of the method that we've used to come up with these matrices. So it doesn't mean that there isn't a relationship we can derive, it just means that because we've used the Euler sequence of rotations, we can't do it. And then we'll remember that if you're doing something, say, like missile aerodynamics, where you can often have theta angles of 90 or high inclination military flight, then, oh great, that's stopped working, excellent. Then, there we go. Then in those cases, you'd need to use one of these other methods. So let's just remember that those are things like quaternion methods, or direction cosine matrices. And again, this course isn't designed to give you everything you need to do to go through flight mechanics, so I'm not going to teach you these two things, but you now know that those are different things that you would need to use in the case where you've got limitations. Okay, so that's good. I think there's one more set of angles that I might just discuss now. If I can get my equipment to keep working, that would be good. Let's try unplugging things and plugging them back in again. There we go. Okay, so in fact, I'm not going to go through this last bit. I want you guys to understand trajectory angles. Okay, trajectory angles, these relate the wind vector to body axes. Okay, so remember the wind vector is our VF, and we go through two different angles. So we go through the track angle, which effectively represents our heading, and then we go through the flight path angle, which we've already gone over. So track angle. It's given the symbol tau, and the flight path. I'm not going to go through this in too much detail. I said I wouldn't go through it at all, but I'll give you a quick overview. I want you to go through this and look in the notes and understand. So if I've now got my Earth axes, XE, Y, and ZE, then we're relating the aircraft flight path vector back to the Earth axes. So it goes through these two angles. And this is always a bit hard to draw, which is why I don't necessarily want to go through this in class here. So we've got this angle, which is tau, and we've got this angle, which is gamma. Now the sequence of rotations we do to go from VF back to Earth axis is we go through the flight path first and then the track angle. It's actually the opposite way round to go from the flight path angle to go from the VF vector to body axes. So remember, going from VF to body, we go through side slip and then angle of attack. Let's go from VF to Earth, we go through the flight path and then the track angle. So the relationship's just the other way around. We go through what feels like a yaw rotation second with this, whereas with the other transformation we go in the other direction, or the other order. So we can just quickly say that UE, VE, and WE. Okay, because we go through this rotation first, we can easily define the VF sine theta. So let's say that's the vertical component in body axis is equal to the magnitude of the velocity vector multiplied by the sine of the track angle, and that means we're going to see the cosine of the cosine of the flight path angle, rather. I shouldn't have said track angle, appearing in these two, much like we see in U and V with the aerodynamic angles, we see the cosine of the side slip angle. And so in these, I'm then going to see cosine tau, sine tau. Okay, so this is just looks similar to the aerodynamic angle relationship, which, remember, aerodynamic angles goes from the VF, or goes from wind vector to body axes. This goes from the wind vector into earth axes. Made a real pig's ear of talking about this here, guys. But I've gone through it really quickly. I want you guys to look in the notes and look at this relationship and just check that you understand it. Okay, so let's just say this one on here is VF cosine gamma. I didn't plan to go through this, which is why my spiel's a bit crap. But I want you guys to go through this in the notes and understand it. The important thing that we've done today is getting these two matrices, because these now, we've got all of these relationships that are going to help us fully describe unconstrained flight. So we've got translational equations of motion, we've got the rotational equations of motion, and we now have this relationship, which helps us to find the anything we measure in terms of angular rates in the aircraft body back to a means that we can use to describe the aircraft's angular position, i.e. its attitude. So this is rate of change of attitude. And this one here is body angular rates. Okay, handwriting is getting atrocious. I'm sorry, I'm just rushing through this last bit. I should slow down, really. I'll slow down for the next lecture because I don't have a time limitation. So that's the aircraft equations of motion fully derived, gone through everything we need. We're going to go through a couple of examples in the next lecture about relative motion, talking about what happens if we've got sensors on parts of the aircraft that aren't the centre of gravity. Things are going to happen due to that Coriolis theorem that we've already derived. And we're going to have a look at just another example of relative motion, which is whether we need to take into account the Earth's rotation or not. So I'm going to pause here, zip together this mishmash of videos that I've recorded as a single lecture, and I will get on with the next one.